The ancients saw the heavens as unchanging, ageless. But they do change. Stars grow old and die. The smallest stars fade slowly like a fire's last embers. Larger stars, however, do not go gently into that good night. In the final stellar battle between gravity and pressure, gravity wins, and the destiny of the star is determined. This is true of all stars, even the one closest to us.
When the sun becomes a red giant, the Earth is going to be uninhabitable. That the oceans will boil away, and instead of nice ocean waves that are going to lap against the seashore, you're just going to have very, very hot mud. Human beings don't survive very well at temperatures of around 1,000 degrees. So I think we're going to have to call it quits.
Our fate, the fate of planet Earth, is bound to the life and inevitable death of the sun.
What we now know is the evolutionary track for a one solar mass star, in other words, a star like the sun. It starts its life as a full-fledged star on what we call the main sequence. It's a place on a luminosity temperature diagram, that's called an HR diagram. It's a place that's characterized by hydrogen to helium burning in the core, and it spends most of its life in the hydrogen to helium burning phase.
Turns out eventually common sense will tell you that the hydrogen's going to run out. And that's what happens 5 billion years from now. At the center of the sun, there will be no more hydrogen to fuse to form helium, and it will have to change its structure rather dramatically. What happens, for rather complicated reasons, is that the central part of the sun will compress and will become a little bit smaller. But the outer layers of the sun are going to become much, much larger. And what you're left with is a small core, which is about the same size that the sun is now, but it's surrounded by this huge envelope.
The reason it's called red giant is kind of interesting in and of itself. First of all, we know that the temperature of the surface of that star has dropped. It's moved to a cooler area, a redder area of the HR diagram. And it must be a giant because we know that lower temperature objects per unit area put out much less energy. Yet what we're looking at is a very bright object. We now know in the interior of the star more energy is being produced.
Now the sun as a red giant is going to expand into the inner part of the solar system. And so some planets, certainly Mercury and Venus, will do a slow death spiral into the middle of the sun and get swallowed up.
Now, this red giant will eventually reach a point where the core temperature, which has been steadily increasing, reaches something like 100 million K, 100 million kelvins. And at that point, the helium core now serves as fuel.
The helium that's now in the center of the star is going to start to fuse and is going to form carbon. It happens all at once, not just gradually from the center burning it out, but all of a sudden, bing. And then what happens is that the sun is going to settle down, it's going to shrink a little bit, and eventually the helium's going to run out.
At this point, the star stops burning nuclear fuel in its core. It only burns fuel in shells around the core. And it becomes unstable. It's a very large star, bigger than the orbit of Venus, and in some cases the planet Earth around our sun. And the outer envelope of the star gets blown off in a relatively mild eruption that forms what's called a planetary nebula, a very beautiful object in the sky.
Planetary nebulae mark the end point in the lives of stars like our sun, relatively low-mass stars that live for billions of years and earn their living primarily by converting hydrogen to helium and then briefly later helium to carbon and oxygen. And when the carbon-oxygen core builds up sufficiently and the star is sufficiently bright, it expels its outer layers.
And as this ejection takes place, someone outside looking at the system sees a shell of expanding gas, And so the end result is a ring-shaped appearance because the thin region that you're looking through looks transparent, while the outer layers, which you're looking through a longer column length, become opaque. So the appearance then is a ringed structure with a central, very bright, exposed core.
Planetary nebulae, as well as mass loss in a more quiescent phase from stars, allows the stars to get rid of their outermost envelopes, leaving behind the carbon-oxygen core. And that then forms a very interesting, dense, compact object about the size of the Earth, which we call a white dwarf.
When the great American telescope maker Alvin Clark ground a new 12.5-inch lens, he tested it by pointing at the brightest star in the sky, Sirius. There was this great blaze of light, and there next to it was this little dot. And he's supposed to have said, "Oh dear, I have a reflection in my telescope." He went back in and he polished and ground and painted the tube black. He went out and looked again the next night. There was the great blaze of Sirius, and there was the little dot. He had discovered a white dwarf.
A white dwarf star is a tiny ball that is just about the size of the Earth. And if you were to take a cupful of white dwarf stuff, if this glass were filled with white dwarf stuff instead of water, I wouldn't be able to hold it here because it would weigh as much as 24 elephants. So white dwarfs are made of very, very dense matter.
The gradual fading and decline of a white dwarf is a very slow process. The planetary nebula remains visible for perhaps 10,000 years. The white dwarf will remain visible for a period longer than the present age of the universe. That is to say, no white dwarf has yet completely died. What happens is that they radiate away the only energy source they have, the thermal energy of the nuclei of the carbon and oxygen, or whatever, atoms in the core, from a surface which becomes cool and is very small, so that the energy is lost very slowly.
Nuclear fusion does not occur inside a white dwarf. So it is able to radiate away only the energy that is stored in the nuclei that comprise the white dwarf. But no new energy can be released through thermonuclear fusion. So the white dwarf simply cools down and becomes less and less luminous, less and less powerful. And eventually, it is simply a rock-like substance, although it's very different from a normal rock that you find on Earth.
And so now what we've done is follow an evolutionary pathway that has tied together a wide variety of different beasts. A main sequence star like the Sun, a red giant, a planetary nebula phase, and a white dwarf. They're all the same.
Not all stars die lingering deaths. For example, a star the size of the Sun, when locked in a close binary orbit, can explode after stealing fuel from its companion. And the most massive stars self-destruct in titanic displays of celestial fireworks.
A white dwarf that forms from a single star will simply cool down over billions of years and eventually become a black dwarf. It will not explode. However, a white dwarf that is a member of a binary system can steal material away from its companion star and thereby grow in mass. This can lead to all sorts of fireworks. If enough mass, enough hydrogen for example, builds up on the surface of the white dwarf, an uncontrolled set of thermonuclear reactions can occur that will cause the outermost material to expand away explosively. And for the star, consequently, to brighten. This phenomenon is known as a nova, a new star. Although, of course, really what we have is a very old star which has been rejuvenated.
Because the amount of material that explodes in a classical nova is only 10 to the minus 4 or 10 to the minus 5 solar masses, and the donor star is of order a solar mass, necessarily novae will repeat. That is, you'll have an explosion, and the donor will continue to drizzle hydrogen and smaller amounts of other elements on top of the white dwarf until another thin layer has built up and it will explode again. Normally, the time between explosions is going to be tens to hundreds of thousands of years. If the donor is a giant, though, it transfers material much more rapidly, and you can build up enough for a second explosion in decades to centuries.
Today, astronomers distinguish between what they call common novae, which are explosions that really are like a burp on a star. The star explodes a little material on its surface, but it remains intact after the explosion and can explode again, and sometimes rather frequently. They distinguish between that and a supernova explosion where the star is torn apart. Supernovae are much brighter, last much longer, and are much more devastating in the life of a star.
If the white dwarf continues to receive material from its companion star and does not blow it all away from itself, then its mass could eventually reach a critical limit, at which point that star becomes essentially the biggest powder keg in the universe. The carbon and oxygen nuclei fuse together explosively into heavier elements, thereby liberating nuclear energy. And this occurs very swiftly throughout the entire star, liberating enough energy to completely blow the star apart. And we believe this is the phenomenon of a type 1 supernova, a supernova whose spectrum does not show the presence of hydrogen.
A type 1 supernova needs a companion to explode, but a type 2 supernova springs from a single high-mass giant.
The larger stars act somewhat differently from the sun, and we're still beginning to unravel some of these riddles. Now, what we think happens is this star becomes a red giant, somewhat like our sun does. It's going to be a little bit bigger. It will become so massive that the core that's left over from the end of the red giant phase is not going to be able to stabilize itself as a white dwarf. It's just too big. There's just too much mass there.
What happens as a star evolves is it goes through a series of fusion reactions. First, hydrogen fuses to make helium. Then helium fuses to make carbon and oxygen. Carbon and oxygen fuse to make neon. The neon, carbon and oxygen fuse to make silicon. Silicon fuses to make iron. So you go in a series of fusion stages, giving the star layers of carbon and oxygen and neon and silicon and iron, with the iron being at the very center and the lighter elements being further out.
The temperature of such a core is so high that the iron breaks down into helium nuclei and neutrons. That means that the pressure in the central part of the star becomes very low, the core collapses, and the outer layers subsequently follow. These outer layers bounce off of the very tiny core that is the remnant of the iron which collapsed. This tiny core rebounds a little bit and imparts energy to the surrounding layers, thereby blowing them off.
The inside of it collapses to form a very strange object called a neutron star. The energy released from that collapse causes the outer layers to expand very fast, and the star becomes what we call a supernova. It becomes as bright as the entire galaxy that it's a part of.
Some energy is also required from interesting little particles called neutrinos that are emitted in copious quantities during the collapse of the core and from the new neutron star's extremely hot surface. These little neutrinos go streaming out of the star and help push the outer layers away.
These kinds of supernovae, the type 2 events which show hydrogen, come from younger population of stars. In fact, we know they come from very massive stars which have relatively short lifetimes, on the order of 10 million years, for example, instead of billions of years like the sun.
So what happens to the remnants of a once massive star, its nuclear ashes scattered by a supernova?
The processes that go on in the supernova itself are essential to the ejection of the heavy elements that have been produced by the earlier burning stages, and also in the production of new heavy elements. The iron core collapses to a neutron star, but during this collapse, a shock wave is created that propagates out through the infalling layers outside of the iron core, turns them around and ejects them with velocities of thousands of kilometers per second. Thus, the ashes of all the nuclear burning go out into the interstellar medium and can become part of subsequent stars, like the Sun.
We see in the very oldest objects in our solar system traces of elements that we are confident are made in supernovae. Meteorites are the oldest rocks in the solar system, and within meteorites there are little components, little mineral grains that are almost as if they came right out of some exotic place like a supernova or a massive star, because they have compositions that are different than the average composition of the solar system, but compositions that are just like what we could have predicted would have been made in these stellar events. Because of that, some people have said maybe a supernova, the shock wave from it, would trigger the formation of new stars. And our sun might have been just one of those stars that would have been triggered by that shock wave.
Supernova remnants are the remains of stars that have exploded. What we see are gases expanding out at tremendous velocities, thousands of kilometers per second. When we take spectra of these remnants, we find that the gases are enriched in heavy chemical elements, such as iron and oxygen. This shows that supernovae do indeed produce the heavy chemical elements of which we are made. The iron in the hemoglobin of my blood was definitely made in a supernova explosion, and we can see that by studying these remnants.
Supernovae have been observed at least for the last 2,000 years. In 1572, Tycho Brahe, one of the great astronomers of all time, was coming home from his laboratory, and he looked up at the sky and saw near a familiar constellation, Cassiopeia, a new star that hadn't been there before. And he was so taken aback. In those days, new stars were not supposed to appear in the sky because the heavens were supposed to be changeless. And he stopped people on the street and they asked them whether they saw the new star. They all could see the star, of course, but I think if they weren't astronomers, they didn't know its significance. It was seen again in 1604, a phenomenon like that, 32 years later, when Johannes Kepler wrote about a new star that was seen in the sky.
For almost 400 years since Kepler, astronomers watched and waited for another nearby supernova event, but none was seen until 1987.
If you had asked an astronomer which star in the Large Magellanic Cloud was going to blow, this would not have been on anybody's hot list of stars that were about to go bang. That it was a star, there are thousands like it in the Large Magellanic Cloud, and just what was it about this star that was going to make it blow, we're not exactly sure.
February 24th, 1987 was a day that astronomers will long remember. Actually, a night that astronomers will long remember, since we do most of our work at night. On that night, an astronomer named Oscar Duhalde, he was the night assistant on a telescope at Las Campanas Observatory in Chile, went out to stretch, take the night air, and look up at the sky to check to see whether there were any clouds in the offing. And he looked to the south towards a nearby galaxy called the Large Magellanic Cloud and saw a bright object which he hadn't seen the night before. What he didn't know at the time was that he was the first person to see a supernova with the naked eye since Kepler did 383 years earlier. About 2 hours later, at the same observatory, Ian Shelton, an astronomer from the University of Toronto, developed a picture he had taken.
He was taking photographic plates of the Large Magellanic Cloud. He'd taken one the night before, but he wasn't pleased with the quality of it. And so he decided, well, he was going to take another one. the next night. When he took that photograph the next night, he noticed that there was a star there that shouldn't be there. And so he immediately grabbed the plate that he'd taken the night before, he looked at it, and the star wasn't there. And so he looked at it and he said, "This star's bright enough, I should be able to see it with my eye."
So they all went outside and looked at it and realized that they had discovered a supernova. They telegraphed their results to a central telegraph bureau in Cambridge, Massachusetts, and within a matter of hours, the entire astronomical community around the world was talking about the naked eye supernova, the Large Magellanic Cloud supernova, the supernova that we'd been waiting for almost 400 years.
From earlier photographs, astronomers were able for the first time to identify the star that had exploded, a blue supergiant 20 times more massive than the Sun.
Supernova 1987A was an object that occurred about 160,000 light years away from us. This gave us an unprecedented opportunity to test theories of supernovae against observations.
We actually saw the results of the explosion at the exact time that the explosion and collapse of the star to a neutron star occurred. Now, this is very difficult, of course, because when a star explodes, what goes on in its interior is quite hidden to us. The star is opaque, actually, and you can't see the fact that the interior is in turmoil. But during a supernova explosion, what happens is that a star produces a flood of tiny particles which have virtually no mass and virtually no interaction with matter at all. These particles are called neutrinos.
So we expected those neutrinos to play a major role. And some of us, namely myself, had been involved in vast theories that predicted how a supernova worked, depending on these neutrinos. But neutrinos, I remember Fritz Zwicky saying, neutrinos, I never heard of such a thing.
It turns out that in February 1987, there were two large neutrino telescopes on the Earth. At 7:35 on the 23rd of February, 1987, these two neutrino detectors detected between them 19 neutrinos going through. This was a veritable flood of neutrinos passing through the Earth.
The detection of neutrinos from supernova 1987A, I think, was one of the most exciting things in modern astrophysics. It was the first time we detected unambiguously an extrasolar system neutrino signal. We've known for a long time, theoretically, that the bulk of the energy in a supernova explosion would come off in neutrinos rather than in light. In fact, over 1,000 times more energy would be coming off in neutrinos than in normal light. The nice thing in supernova 1987A was that we actually detected those neutrinos. We detected the main thing that was going on in the supernova.
So now you felt secure about going after many other guessworks about supernova. One of these, for me, that was equally important to the neutrino emission was that the light curve of 1987A showed the characteristic decay that we had predicted of the radioactive decay of the primary endpoint of nuclear synthesis. It turns out to be nickel-56, which decays to cobalt, which decays to iron, all in a matter of months. That this decay signature was seen in the light curve.
The other very important prediction that was confirmed by observations of supernova 1987A was the nucleosynthesis of extremely heavy elements, iron and even heavier, during the explosion. Telescopes sent above the Earth's atmosphere detected high-energy photons called gamma rays that are emitted by radioactive nuclei of nickel. These atoms, these nuclei, could not have existed prior to the occurrence of the supernova because they don't live very long. They don't live more than a few years. Their presence in large quantities immediately after the supernova shows beyond any reasonable doubt that heavy element nucleosynthesis did indeed occur during and after the supernova explosion.
The history of our civilization spans some thousands of years, and the archaeological record goes back for humanoids perhaps millions of years. But the atoms of which we are composed, which are the same sorts of atoms that make up all life and indeed our own planet, are much older. They're as old as the stars themselves, billions of years old. The massive stars only live for maybe 20 million years, and then they die as supernovae, and then another generation of supernovae is formed, and this process continues. And each time you go around the cycle, you make more heavy elements, mix them with the interstellar medium, where they form the seeds for subsequent generations for stars. And so the iron, the oxygen, the calcium in our own body is the debris, in some cases previously radioactive fallout from stellar explosions that happened 5–10 billion years ago. So we literally are the progeny of the stars. We're made out of the atoms that were produced as stardust in these giant explosions.
Different stars die different deaths. Some quietly fade away. Others burst into the heavens, creating new elements and the seeds for a new beginning.